Okay, in this video, we will work through some examples of experiments. This is basically the story of the law of large numbers, and we'll do some examples of experiments in R and see how the law of large numbers applies. Okay, so the basic setting that most of the R projects that we work with will involve is either some sort of a coin toss or a die roll. So first thing you could do is you could define a coin toss. The way you could create a coin toss in R is by just using the property of a function. And what we can do is input the probability of a success for the coin toss. That's what you're going to get for probability of a success for the coin. And then in here, what we can do is we can define what the coin is going to be. So a coin is going to have tails or heads, that is 0 or 1. And the coin toss is going to be performed by using what is known as the sample command. And what we're going to do is we're going to toss the coin by using the sample command, and we're going to sample from the coin a size of 1, and we're going to have replace equals true. This is going to ensure that every time we toss the coin, we are tossing with replacement. So uh, the sample space for the coin is not going to reduce. And then finally, we have to supply the probabilities. So the probability vector is going to be the probability of getting a 0, which is getting a tails, which is going to be 1 minus p and p. Right? So this is going to have the toss. And what we want to do is we want to return the toss. Yeah. And you can do the following. What we can do is if we don't supply any input, we can have a default value of tossing a fair coin. P setting p equal to 0.5 over there is going to be a default value for the coin toss. If I toss the coin once, let's run this code. You notice that if you toss the coin once, I got a tails. Then if I toss the coin again, I got a heads. What I can do is I can look at the coin tossed maybe 10 times. And to do this, we can use what is known as the replicate function. So replicate repeats the experiment 10 times. And here are 10 tosses. So we got a head, 2 tails, and then all heads. And notice this was because we tossed a fair coin. If we wanted to toss an unfair coin, the probability of getting a heads is 0.8. Notice that we will have more heads than there are tails. And we do this 100 times, we will get 100 coin tosses here. Okay. So this is how you repeat an experiment. So we can do the following. We can have an experiment that has 5 tosses, right? 5 independent tosses. The way we can get this experiment is going to be a function, right? And we're going to take the probability of success as p, right? And if nothing is supplied, p is going to be 0.5. And now what we can do is we can have tosses to be replicate the coin toss function 5 times. So you will do 5 and coin toss with input p, and we're going to return the tosses. And this function is now going to give you an output of what's going to happen if you run this function once. So you do 5 tosses, right? And you don't supply any probability of success, you will get the output of 5 tosses. Yeah. And say I plug in probability of success as 8, then I will get these 5 tosses where I'm tossing a coin with having probability of getting a heads to be 0.8. Yeah. You can modify this experiment to have n tosses, so you can play around with this. So if instead of 5, you wanted to toss the coin 10 times, what will you do? The only thing that changes is this replicate function becomes 10. And now you can look at 10 tosses with probability of success 0.8. You will see you will get output for 10 tosses over here. And that is one run of the function 10 tosses. Right? We might, okay, so let's start story with the coin toss. You can do the same thing with the die roll. Say I want to construct a function that rolls a die, right? So this will be a function, and typically now you will be having a n-sided die, 6-sided die, say. Then you will have to identify the die, which is going to be numbers 1 through 6, say, and then the probabilities of the die, right? This is going to be what are the probabilities of getting numbers 1 through 6. And you could have, if it's a fair die, you will have 1 over 6, 1 over 6, 1 over 6, 1 over 6, over 6, and 1 over 6. So these will be the probabilities of getting a success, that is getting a 1, 2, 3, 4, 5, and 6. These are each of those probabilities. And now to get a single die roll, all we have to do is we have to sample from the die a sample of size 1, right? We have to have replace equals true. And finally, the probability is going to be equal to the probabilities that we have defined. So if it was an unfair die, we will have to change this probability vector accordingly for the probability of the die. Now you can return the roll. Okay, so here is this guy is going to be the roll, right? So let's do that carefully again. Not really a mistake, but just cleaning up the code. And that's our die roll. Now look at our die roll function. We roll it, we got a 5 on the die, got a 2, and now we can repeat this experiment using the replicate function. Right, so if you replicate this 10 times, you will get 10 die rolls. Okay, so here are 10 die rolls, and you got these guys over here. These are the outputs of the 10 die rolls. Now you can play with this. You can roll the die, say 4 times. Right, so die roll 4 times. Right, so how will we do this? This is going to be a function. Now this guy is, the input is going to be, there's no input for this function. And what are 4 rolls going to be? The first thing we will have to do is specify. So what we can do is repeat, replicate the function die roll 4 times. Right? And what we want to do is we want to return the rolls. Yeah. And so notice that if you run this function 4 rolls, you will get 4 rolls of the die. So every time you run this thing, this experiment is giving you 4 rolls of the die. So that's the story for our die rolls and coin tosses. We can move a little forward now. So once we have set up our die rolls and coin tosses, so maybe we want to do the following. We want to count the number of heads in 10 tosses, right? So then let's have, we have already defined a function 10 tosses. So let's define heads in 10 tosses. Right, so heads in 10 is going to be now a function. What will it do? This function is going to do the following. It's going to perform the experiment of tossing the coin 10 times. So 10 tosses is going to be 10 tosses. And then we have to count the number of heads in 10 tosses. So let's look at this guy. So how do we count the number of heads in 10 tosses, right? So here is an example of 10 tosses. So say I performed 10 tosses once. So these are ones over here. And if you want to count the number of heads, all I need to do is take the sum of this vector, which is going to give me the sum of all the ones, which is exactly the number of heads in 10 tosses. Yeah. And notice that every time I repeat this experiment, this thing changes, right? So the sum changes. So if I perform this experiment here, what I need to return is the sum of the tosses. Now you can see this heads in 10 tosses. Heads in 10. So if you perform the experiment once, you got 6, you got 5, and so forth. Right? So heads in 10 is really the binomial experiment over here. And if I want to understand the binomial random variable, I would want to perform this experiment many, many times. The law of large numbers says is if you repeat this experiment many, many times, and then take the average, I should get the probability, I should get the expected value of the number of heads in 10 tosses. Yeah. So that is something that you can do. So you can replicate this experiment. Right? So if you set replicates to be replicate many times. So let's replicate this 10,000 times, heads in 10 tosses, and we get the following output. And now what the law of large numbers says is the average of the reps is exactly going to be the average of the binomial distribution with n equals 10. And in this case, p was equal to 0.5. That's the probability of a success. And that's something that we can calculate. Okay, so here is p. I can modify this function to have p. And there you go. Notice that that's the sample mean for the binomial distribution with n equals 10 and p equals 0.5. That's exactly close to 5. Okay, so that's the law of large numbers at play. And now you can calculate the variance of the reps. And you will get the variance, which is n times p times 1 minus p for the binomial experiment. So you can play around with this. Okay, so that gives you these guys over here. What we can even do is calculate the empirical probabilities. So how do you calculate the empirical probabilities? So I can use this table command and put these reps in a table, and I will get the relative frequencies of 0 in this experiment. So you got 0, there were 0 heads in 0.14, 14 trials. There were 5 heads in 2,416 trials. What I can do is I can calculate the relative frequency by dividing this by the total number of trials. And this is the probability, empirical probability distribution table. So I can round this off to say 2 decimals. And we get the empirical probability distribution table that looks something like this. So now we can move around these different probabilities and you can play with these empirical probabilities. Yeah, so let's do a more specific example. So say I was just working with a coin toss, right? So say I was tossing a coin 1,000 times, right? So if I do replicate to be equal to replicate, I want to toss a coin. right? So say I toss a coin 10,000 times, coin toss with probability of success equals 0.8. So if I toss a coin with probability of success 0.8, then the law of large numbers tells me that the mean of this thing, right? This is a Bernoulli random variable. The mean of all the coin tosses is exactly going to be close to the probability distribution, the probability of getting the heads, which was 0.8. So this is the law of large numbers at play. And now you can do the following. We can calculate our relative frequency plots as follows. So I can do the following. So let me give you the code, and then you can play around with this code for all the other examples that we are working with. Okay. So say I take B to be 10,000 and I want to replicate, say, the coin toss experiment, right? Say P is equal to 0.8. And then what this thing does over here is this slices the first I iterations of the replicate. So first I slots of your experiment, and then it's calculating the ith sample mean. So the mean over here is first slicing your vector reps up to the ith index, and then the mean is kind of calculating the average up to the ith index. And then it's putting that average into the ith position in this vector y. Okay, and if you run this command, what you end up getting is the following. So you are ready to, once you do that, you're ready to use this code over here, which is going to give you the plot of the relative frequencies. And as you can see, the relative frequencies eventually start stabilizing around 0.8. So I want to put a horizontal line at 0.8, and you can see that that is where we will have the relative frequencies stabilizing as the samples become very large. Okay, so that is the first part of our story over here. So there is another experiment that we can do. I mean, I believe calculating the sum of the numbers appearing on top of a die as an exercise for you. But here is another example of experiments that I will work. Say I want to calculate the number of failures or the number of tails until a certain number of successes, right? So say this is the random variable that I am interested in calculating. So say R is equal to, suppose R is equal to 5 or say 6. Yeah, so I'm waiting for R 6 successes. Yeah, and I'm counting the number of tails until the rth head. Okay, so to be able to do this experiment, we now need some additional tools. So we need what we call while loop. So let's calculate the what's going on over here. Okay, so let's count. Thing is off. Okay, so let me do thing. Okay, sorry. Okay, let's get back to relative frequencies, calculate the number of trials until the art success. So how do we calculate failures or tails till sixth head, right? So I want to count this guy, so I will say I am tossing a coin with probability of getting a heads to be P. That's the coin that I'm going to toss. And now, what is it that I want to do? I want to keep tossing this coin until I get uh, that get 6 heads, right? So let's do the following head count. So we want to count the number of heads. So head count is going to be 0. We're going to set this to be 0. Tail count is also going to be 0. And what we want to do is while head count is less than or equal to 6, right? I want to do the following. I want to toss, right? So toss is going to be coin toss with probability of success P, single coin toss. And what I'm going to do is if, right, toss is equal to 0, I'm going to do head count equal to, tail count equal to tail count plus 1, right? Else, I'm going to do, what am I going to do? Head count. So which head count is going to equal to head count plus 1. So I'm going to add to a head count. So basically what this while loop is doing is as long as the number of heads is less than or equal to 6, I'm going to toss a coin. And if the coin toss comes down to a tails, I'm going to increase my tail count by 1. If the coin lands heads, I'm going to increase the head count by 1, right? And I'm going to stop the moment my head counts become greater than, strictly bigger than 6, right? So if head count increases to 7, I have to stop. Yeah. So, and what I need to return at that point is the number of tails until I got the 6th head. Right. So I need to return the tail. This will do it correctly, right? So less than or equal to 6. So while head count is less than or equal to 6, so this counts the number of failures. So the moment head count becomes 6, I'm going to right. So I'm going to come out, I'm going to go up. It realizes that it is exactly equal to 6. I'm going to come out, and that's what's going to happen. What is wrong over here now? So while, sorry, I think less than or equal to, I think is that what this is? While head count is a minute. So x is less than or equal to, right? I think I should have this to work. Head count is less than or equal to 6. This should work. It's wrong here. Oh, I see. This is wrong. What's going on? error unexpected equal to toss. Oh, toss is equal to. So, okay, so this is exactly the negative binomial dish experiment, and now you can look at tails till the sixth head. If you toss this coin with probability of getting heads is 6, you get 2 over here. Now you can repeat this with 0.5, say. Perform this experiment, and these are the number of heads that you get, and you can calculate the empirical expected value and variance, and you will see that it matches the theoretical expected value and variance that we have calculated in class. Okay, so that's the basic story for the experiments in the context of this R project. The other thing that I want to touch upon is this experiment about Bayes' theorem. So in one of the videos that I have shared with the empirical in my asynchronous videos, I've pointed out this witness experiment where there is a hit and run situation, and a witness claims that it was a blue cab. There are two kinds of cabs, and the witness claims that it's a blue cab that is at fault, and we calculated the posterior probability of the blue cab being at fault given the witness testimony that it was the blue cab that was at fault. Yeah, and we calculated this formula for the posterior probability. Bayes' paradigm tells us that what we can do is we can take this posterior probability and put it in the prior probability, replace probability of having a blue cab at fault by our posterior probability, and keep repeating this experiment over and over again until we arrive some equilibrium. In this case, the equilibrium that we're looking for is some threshold probability to believe that the blue cab was at fault. And the experiment, what we're going to do in this R project is basically calculate various graphs attached to this experiment. So the first thing you can do is you can calculate the Bayes function. So it's basically this function put into a function formula over here. And if you run this code chunk, you will see that Bayes formula kind of gives you this updated probability for the probability of the blue cab being at fault given the witness testimony. Now, what we can do, and something that you have done in the homework problems, is we notice that if the witness reliability was greater than half, then your belief that the blue cab was at fault, the posterior belief, is going to be higher than your belief that you originally started out with. And that is something that you can see in these plots. Yeah. So if you run this code, you will see how the belief is constantly increasing. So these dots are corresponding to how your belief is increasing. And at some point, the probability that you would believe that the blue cap is at fault, the posterior probability, eventual updating is going to go over this threshold because your witness testimony, you believed the witness with probability, in this case, probability 0.6. This is the witness reliability. So witness reliability bigger than 0.5 meant that your posterior probabilities will keep on growing. Yeah. And at some point, they kind of get above a threshold that you might be interested in. In this case, in our example, the threshold is 0.9. Okay, so this is the threshold that we are interested in. So we can repeat this experiment with this guy over here, and you notice that P equal to 0.4 means that you had a bad witness. And if you have a bad witness, your belief that the blue cab was at fault is going to keep on decreasing. It's like saying that you had a colorblind witness coming out and saying that the blue cab was at fault, but the fact that the witness was colorblind kind of makes the testimony irrelevant, right? And your belief in believing that the blue cab was at fault, given the witness testimony, is as a result going to be less than what you originally believed in, without the information from the witness. So you can perform this experiment, modify the code accordingly to see the plots over here, and you will notice that the plot will have the reverse thing. It's going to start at a high place and it's going to go towards 0. Question would be, okay, now how many witnesses do you need, right? And to be able to do that, it's a simple counter problem over here. So you will have to set up a counter. You start with counter at 0 and you count the number of witnesses needed, and you notice that it's 29 witnesses. The 29th witness is going to hit you above the threshold, and you can notice over here is 30, and 29th witness is what is taking you over the threshold of the red line, right? And that's exactly what you calculated in your original calculation. You can modify this. So it can so happen that maybe instead of just one witness or witness with a fixed probability of a witness reliability, you could have witnesses of two different reliabilities, right? So there could be one witness that has a reliability that is greater than half, another witness that is whose reliability is less than half, right? So here are the two reliabilities. P1 is the reliable witness, and P2 is a witness that is unreliable. So if you had witnesses with these kinds of reliabilities, then our problem is going to be a little more complicated. Yeah, so you can see that we can start with the first assumption that constantly you're having a witness with reliability that is a reliable witness on all the even tries, and you have an unreliable witness on all the odd tries. Yeah, so I mod 2 is kind of, this is checking if I is an even number, so modulus. And if you run this code, you will notice that our plots are going to look like this. So our reliability, I mean, the reliable witness is increasing your propensity to believe that the blue cap was at fault given the witness testimony. The unreliable witness is reducing it. Then you go up, then you come down, go up, come down, and so forth. And at some point, you're going to hit the threshold because, so this has to do with the fact that your reliable witness was quite reliable. It was much more higher than 0.5. So if this number was close to 55, say, for example, your graph would take a much longer time to hit the threshold that is required for you to believe that the witness is at fault, the blue cab is at fault. For example, if your reliable witness was even more reliable, notice that the amount of time you have to wait until you hit the threshold decreases. It's now closer to 20. Yeah. And you can see this. You can perform this counter problem, count the number of witnesses needed. You can run this code and notice that you need only 20 witnesses if your reliable witness was having witness reliability 80.8. If the reliable witnesses were having reliability 0.9, you will even need less number of witnesses. It's 12 number of witnesses. Yeah. So play around with this, see the different things you can interpret with this code and with these plots. Yeah. Finally, instead of having reliable and unreliable witnesses kind of constantly alternating one after the other, we can use the sample command to choose witness reliability, right? So we have two types of witnesses that could show up, one with reliability P2, one with reliability P1. One is a reliable witness, the other is an unreliable witness. And we will kind of, at every stage of our Bayes problem, we are going to choose a witness with one of the two reliabilities. Yeah. Then we are going to update our probabilities with this witness that we have chosen. Again, you can see, you can perform this experiment. And now, unlike the last one, you will notice that the graph is not like this, where it's constantly going up, right? Because we are sampling, sometimes it will go up and sometimes it will keep going down. Yeah, so you can look at this over here. So if this was 0.6, for example, and we are sampling, you will notice that the graph plot will look something like this. It's going up, going down, and the number of trials you have to wait for will increase. So notice in this plot, we are still at 0.4, right? And the number of witnesses that you will need in this context will be much more. So here is the counter problem that you can count the number of witnesses. And here you need 115 witnesses to go. So if you plot this guy with 120, yeah, you will see that you will have better graphs. Use this. And here you can see your plot's kind of increasing, decreasing, it's increasing, and it's keeping on decreasing over here. Then it starts going up. It's still not hit the red line. Yeah. So you can use this as an experiment and calculate the expected number of witnesses that you might need. Yeah. So in this iteration of this experiment, you got the threshold at about how many 85 witnesses or so. Yeah, and that's constantly going to change because we are sampling over here. So the sample kind of is making it a little probabilistic as opposed to deterministic in nature, what kind of witness you will have at every iteration. So it's not guaranteed that your probability that the blue cab is at fault, given witness reliability at every stage, it's not guaranteed whether it's going to go up or down. Now, because of this sample command, it could go up or it could go down. Yep. So that's the story with this problem over here. And now you can, I have shown you how to work this out. You can work with 4 witnesses. All that's going to change now is you, out of the 4 witnesses, you have 2 witnesses that are reliable and 2 witnesses that are unreliable. And now you're going to sample out of the reliable witnesses. You're going to sample out of the unreliable witnesses, and you're going to play around with this. So there will be different for and while loops at play. So give it a shot, see how it works out. Okay. So the graph that you will get are something like this. So you want to aim to get a graph that eventually goes beyond the red line, which is the threshold that you are interested in. So this is kind of an interesting application of our witness reliability problem. So, I mean, you can play around with this. So the idea is always to take this as a starting point and see what are other interesting things that you can work with in this context. Okay, so 2 things that we have covered in this video: the law of large numbers, kind of setting up experiments, calculating empirical probabilities, and then working with this problem of Bayes' theorem about witness reliability. That's all. Have a good time with this project, and we'll see you around.